project. So, Rafael, you want to introduce Yanke?
Oh, sure. I'll be happy to. I should have prepared for this, but anyway, I also don't come to these meetings too often, but I'm happy to have Yanke on today with us. He's just freshly back from an internship in California, and about a year ago we met here actually, and we discussed this idea about dealing with event files and using event files of individual X-ray sources to identify certain types of time domain anomalies. And I guess we have been thinking about this problem from many angles. And Yanke has come up with a very interesting approach that uses a Poisson Process AutoDecoder to process the event files and create meaningful representations of time domain and spectral aspects of X-ray sources. So that's what he's gonna tell us about. Thank you, Yanke.
Yeah, I'll get started. Thank you, everyone. I was going to talk about that myself because the last time I was here, I had a very interesting discussion with Rafael and Ashley, and that's what started this project a year ago. Oh, by the way, I'm a fifth-year statistics PhD at here. So I'm going to directly jump into the motivation. So we have massive X-ray data from all these X-ray surveys and detectors. And X-ray data, what I mean is basically event files. An event file, although it has some other measurements, I'm going to do some simplification and only consider it as a list of photon arrivals, where each arrival contains a time, the arrival time, and an energy, which is the energy of the arriving photons. So an event file basically means a list of photon arrivals. So to visualize what these event files might look like, here I'm doing some histogram of the arrival times, ignoring the energy for now. So we can see that there's different type of interesting event files happening here. So here is like a flare where there's a certain burst of photon intensity. And here's a dip where there's a certain decrease of photon intensity. And this periodic source where there's rise and falls of intensity. And there is this.
Excuse me, could you share your screen so we can see it on Zoom?
Oh, you're not sharing your screen?
He's sharing.
Yeah, he's sharing.
Oh,
I can see it.
Sorry, I may have my setup not correct. Okay, I apologize.
Oh, okay. And also, this one is a less interesting event where basically the underlying rate is non-varying. And I should mention that it is pretty common in astronomy literature or like community to assume that these photon arrivals comes from a Poisson process, where basically we think there's an underlying true Poisson rate, where we call the light curves. And these arrivals are a Poisson process with that underlying rate, which means that these arrivals are stochastic. For example, you can see here in this non-varying sources, where we think that probably the underlying rate is not changing, but we see there's noises in the arrivals. At some point, there's like one or two arrivals, and at some other time, there's no arrivals.
Yanke, can I ask a quick question? Why do you call that non-varying? I mean, it's the difference between that and the others, or simply that there are a lot fewer counts in that.
Yeah, it's both lower count event, and I call it non-varying because compared to others, where we think probably there's some underlying physics happening here. For this event, I mean, I think, I'm not an astronomy person, but I think this is probably just like a low count event without changing the rate.
Homogeneous.
Sorry, say again?
It's homogeneous.
Homogeneous, yeah.
Well, is it? I mean, calling it non-varying is a very definitive statement, right? I mean, it's like you're saying that, for example, there could be, I can, just left to my own devices, I would say that there was a higher intensity, and then there was a drop, and then it went up again, right? I mean, but why call it non-varying?
I mean, is the particular group of the particular groupings of photons in this particular representation actually showing variability? I mean, I think I agree with Vinay that the fact that we have few photons with some fluctuations does not necessarily mean that it's non-varying. I think you would need to run a test to decide whether it's varying or not, statistically speaking. Maybe what you're trying to say there. Yeah.
This is real data, or is this simulated data?
Real.
This is real data.
Because it was simulated, then you would know what you put in, right?
Exactly.
Yeah.
Yeah.
It's-
Actually.
Can I just
Yeah,
say it looks consistent with a homogeneous Poisson process. Sure, it might not be one, but if you sample data from a homogeneous process with this intensity, I don't think this would look at all unusual.
I agree with it, yes. I mean, I'm not saying it is not non-varying, I'm just saying you can't tell just by looking at it.
Yeah, I agree. I shouldn't call it non-varying.
Or you could have picked a bigger source with a flatter light curve, perhaps.
Yeah.
But anyway, sorry. Continue.
Yeah, I should also mention that this is just some arbitrary histogram, as if you shouldn't think of it as the real light curve anyway. So yeah, back to what I was saying. So we have massive amount of these kind of X-ray data, and it's just impossible to look at all these histograms by eye. So one would like to do some learning automatically. By learning, I mean different kind of tasks. For example, source type classification. So for example, this FLIR and this periodic source are obviously different type of sources. And we would like to classify those if we can directly operate on these event files. And obviously anomaly detection, we would like to, for example, detect these FLIRs and dips using some automatic pipeline. I'm going to talk about some previous approaches to deal with this kind of automatic learning. So previous approaches include both supervised and unsupervised learning. By supervised, I mean, besides event files, we also have some supervised labels, for example, the class types or other things. By unsupervised, I mean, we're directly operating on those event files without any supervised labels. So for both supervised and unsupervised, one line of work do the learning by creating some manual features. These manual features often requires domain knowledge, which I'm sure most of the people here have more than me. And they also might require some time-consuming pipelines, and sometimes more than one. So here I'm taking like a screenshot of the features selected from one of the previous paper. It includes the hardness ratios, which are just some ratios of the photon counts in different energy bands. It has this value called dBKT, which, as they describe it, is the temperature of the best fitting model of some type. It is obviously a physical model, which requires domain knowledge. They also have this variable, which is also the best fitting photon index of some physical model. And they have these three variables, which are variability probabilities, variability ratios, indexes of the output of the Gregory-Loreto algorithm, which is actually a statistics algorithm that I'm going to introduce briefly. But like the takeaway here is that for all those manual selected features, they all require either domain knowledge or model fitting or both. For another line of work, it doesn't create the features by hand. Instead, use deep learning to create representations.
So maybe I would interrupt to say, I mean, when you say by hand, what you actually mean is just with some sort of forward modeling approach that has taken the event files as an input and produced some quantities that are derived, you know? So for example, the variabilities are obtained from the Gregory-Loredo algorithm. The hardness ratios are taken from some Bayesian analysis of the distribution of the energies of the photons. So I just want to clarify that that's what we mean by binary features. They're not necessarily just something very easy and quick that you do with the data. They usually involve these complicated algorithms they use, and that's what it takes to generate the properties in the catalog, for example. But so right.
Thanks for the clarification. By hand is like
in a way they are quantities that are meaningful to the human, right? Variability or you know, hardness ratio. How is the spectral shape of these objects? They are meaningful to us. Does that mean that they are the best possible representations of the data? I think that's what you're testing here.
Exactly. So another line of work learns these features via deep learning, like without any specific model assumptions. Like different deep learning models has been used, for example, CNN and RNN. But I should emphasize here that all these deep learning models, their input is the reconstructed light curve instead of the raw event files. Here, the light curve basically means the underlying Poisson rate function that is reconstructed. So they take this reconstructed rate function. I'm going to use the light curve word from now on. Take this reconstructed light curves. They sample it at some evenly spaced points, which gives you a time series, and they can use this time series for deep learning approaches. So the obvious drawback here is that you first need some light curve reconstruction algorithm before inputting to these deep learning models. So for light curve reconstruction, obviously, the most naive way is you can just bin the event file like what I did here. But obviously, it creates some artifacts. For example, here, we think this might be a homogeneous Poisson process, but if you bin it, you see that there's 1s, 2s, 3s, and zeros elsewhere, which is some artifact variation if you just bin those event files. And now there's like a more complicated Bayesian approach, which I think is pretty rigorous, called the Gregory-Loredo algorithm. I'm going to talk about it like very briefly. So what GL algorithm does is that first they consider all the hypothesis light curves, which is all the stepwise light curves up to a certain frequency. For example, you can propose a constant light curve. You can propose a two-step light curve up to, I think people usually do like up to 20-step light curve. And you put some prior probability on those different light curves. And for each of the proposals, you compute the Poisson likelihood of that given the event files, which gives you a posterior probability. And then you can superimpose all those proposals weighted by the posterior probability. And then it gives you a light curve reconstruction result. Here is actually a visualization of the Gregory-Loredo algorithm, where this dashed line is the true light curve. And you see it also gives you an upper and lower bound for the reconstructed light curve. So,
so here the dotted line is a simulated actual variability pattern, or what is?
Yeah, I think the dotted line is the simulated actual light curve. I'm not showing the event files here, but they use those simulated event files to reconstruct via the Gregory-Loredo algorithm. So I would say it's a pretty good result, but you can see it's piecewise linear because the Gregory-Loredo algorithm can compute at most as, let's say, 20 different stepwise light curve of 20 values. because it's a pretty computationally expensive algorithm. Like I said, the first drawback of GL is that its resolution is limited due to computational complexity. And the second drawback, which is not necessarily the GL algorithm, but the whole pipeline, is that if you use the GL algorithm to reconstruct the light curve first, and then use the reconstructed light curve to do some deep learning approach, it's kind of disjoint. It's not like learned end to end. So that's the second drawback.
What do you mean by carefully defined prior?
Actually, look at the Gregory Loreto paper, and the prior is just you have 1/2 probability that the light curve is constant, and 1/2 probability that the light curve is variable. And for those variable light curves, they just put even probabilities for like light curve of 2 values, 3 values, up to 20 values. So you can call it carefully defined, but like it has some assumptions there. Yeah.
Yeah, I have a question about the priors. Can you define you can define it like with whatever assumption you have for like how a variability light curve will look like, or how a fair light curve will look like. Are those like flexible, or they are like predefined in some way?
Within each proposal, the specific values are like uniformly prior. For example, like for constant light curve, they put a uniform prior on the true value. Yeah, but there's definitely some assumptions put in, which may or may not be true.
Is the computational complexity coming from testing the different hypotheses, or from another step?
Basically, the larger the number of values for the stepwise light curve, the higher computational complexity, because you need to consider, say if you have a 20-step function of the light curve, then it's basically a 20-dimensional Bayesian problem.
Okay.
Yeah, and it goes higher, basically exponentially.
I think it's interesting that you're putting it in terms of priors and posteriors. I have to confess that's not the way I was interpreting the Gregory Loreto algorithm myself, but maybe it's worth having the little discussion. Like the way I understand it, and I might be wrong in my understanding, is you consider, given a list of events, you consider all the possible binnings of those events, right? So you consider binnings of different lengths basically, and then for each bin size you compute the probability that the given data would be distributed in those bins the way you observe it, assuming basically that it was just by chance, right?
Exactly.
It's like the odds that these particular distributions of the events would be in those bins, and then you compute that for all possible binnings. And based on those odds, you define some certain weight of that particular binning, and then you sort of add them up, weighted by this factor to construct the final light curve, right? That's I think that's how I understand it.
Yeah, that's an interesting way, but I think those are
in that respect. What would be the prior? The binnings.
The binnings.
The binnings.
Like
okay.
You assume those binnings are like equally probable before you see the data.
Right.
That's the prior, and by binnings, like it's basically equivalent to a stepwise light curve, because you assume within a certain bin the rate doesn't change. Yeah, and the likelihood is just computed by how likely those bins are happens by chance or it's actually changing. Yeah, it's another way, equivalent way of understanding.
Thanks.
Can I ask just quickly, computational complexity? What do you mean? Is n squared too complex, or is n squared? Okay, I forget what Gregory Loreto is, but
I actually don't have that in by hand right now. Yeah, I need to check it out, but I think it's definitely not linear. So even if it's just n squared, if you want to consider smooth light curve, for example, of like 400 stepwise light curve, that would be pretty expensive.
Okay, thank you.
Yeah. Right. So these are basically all the previous approaches for X-ray sources learning. So in this talk, I'm going to propose a learning pipeline that, first of all, is fully unsupervised. We don't need any labels to do the learning. It respects the Poisson nature, meaning that it doesn't overfit to the artifact if we just do the naive binning, for example. It has infinite resolution, meaning that conceptually it can reconstruct a very smooth light curve without those artifacts created by Gregory-Loreto algorithm. It is end-to-end, meaning that it does light curve reconstruction plus representation learning at the same time. Hope you guys are still interested in this pipeline. So now I'm going to introduce this pipeline like piece by piece. So as a starting point for simplification, I'm going to ignore the energy marking and just consider the set of arrival times for the event file. This result is actually pretty standard. So like suppose we have a real light curve R, then the likelihood of observing this set of event file given the true light curve is given by this formula. So we have a first term where it's just a product of the light curve values at those arrival times. And we have a second term, which is kind of a negative regularization of the integral of the light curve over all the over the entire time. So this light curve, this likelihood, one usually likes to maximize the likelihood. But if we rephrase it as a minimization problem, we can think of it as a loss function to minimize. So I'm using the negative log likelihood to minimize as a loss function.
Can I ask a quick question? So you said that you got infinite time resolution. So does that just mean that the T are essentially floating points, so it can be any number?
T, yeah, exactly. The small t can be any number. But this large T is like how the lifespan of the event. Yeah. But like in practice,
Ti themselves are when the photons are.
yeah, Ti are like very precise time values like of any resolution. But I mean, in practice, if you want to approximate this integral, you obviously need discretization. But what I mean is that you can use like any number of discretization for this, like theoretically, do like any resolution.
No, so the thing that confused me is that you got a product of RTI and an integral in the exponent. So I would have expected, wouldn't that be better if it were a sum?
Well, no, because these Ti are like arrival times,
Right.
and this T, it can be any other time. It doesn't have to be arrival times.
But for that, you need to know how the R is defined.
Yeah.
In between.
Yeah, exactly. I'm assuming here we have a true likelihood, but like it's undecided yet.
Does this likelihood function integrate to 1?
It doesn't. No, it doesn't. You mean integrate to 1, like integrate with respect to what?
I'm trying to understand the exponential term. You were saying it's a regularization term, right?
It's pretty hand wavy. Yeah, I'm not sure what's the best way to explain this, but it's just like a pretty standard Poisson likelihood. Okay.
Yeah, and astronomers call it the catch likelihood. This is a standard likelihood for event data.
Sorry,
You're breaking up a little bit. Is that David? You're breaking up a little bit. Can you repeat it?
I think that was
Jeff? Yeah, okay.
Sorry, this is the standard catch Astronomers call this the CHASC likelihood. It's the standard likelihood for event data.
Okay. Yeah, thanks for pointing out. Yeah, I
mean,
think it's pretty
just, can I
standard.
just to translate that for statistics, it looks like a Poisson distribution. It's e to the minus lambda and then lambda to the x, but the x's are all ones or zeros.
Yeah, that's how you can derive this for events.
I think I might need a power. Is this mine? Sorry, let me plug in.
We need plug in this. Yeah, power. Oh, is this the break we were hoping for?
Yeah, let's just take that.
And there is a drink.
Yeah, coming at the perfect time just for the food.
Oh, no, we just starting the installation.
Are they able to hear us now, the Zoom people?
Yeah.
Okay. Just taking a small break for getting the food. All right.
You can also do the plug.
There's one here.
Right there.
Oh, there's one down there.
It's not conveniently designed, but.
There's
Yeah, I'm fine.
No,
It's working.
go ahead.
Sure, yeah, let's resume. So a quick recap. Now I have a raw event file of time arrivals. Given that we assume there's a real light curve, we can compute the likelihood of this event file given light curve. It's just the standard inhomogeneous Poisson likelihood that we're doing here. And we do the negative log likelihood to rephrase it as a log function to minimize. But the problem is that likelihood only is not enough. Because let's consider, for example, this event here. Suppose I'm fitting a light curve that has very large values exactly at those arrival times and has 0 values elsewhere. Then if you look back this likelihood, this is going to be very high because I'm having high rate at exactly those arrival times. And because I'm having 0 elsewhere, then this is going to basically be 0, or be a very low value. So this likelihood is going to be very high. But
Can I just somebody has their hand up.
People can ask.
yeah, just feel free to interrupt me anytime.
There's a message in the chat.
Good, check the chat. No, that's
Hey, if you have questions, just ask now.
Yeah.
They put their hand down, so maybe they didn't really want to speak.
Oh, okay.
There's quite a bit of chatting about people not being able to see the screen. I can see it, but several people can't, so I don't know what's going on.
Oh, well, can you stop and
Let's
restart?
reshare, yeah.
Can people see the screen now?
Yes, that works now. Thanks.
Okay.
Okay.
Can
Yeah,
you still see? Just is everything okay with the screen share?
I think so.
Okay, all right, let's continue.
yeah. I was saying that this likelihood only is not enough because it creates some singularities, where the singularities, for example, happens at very large rates exactly at arrival times and very low rates elsewhere. So we need some other kind of regularization in order to fit like a normal, reasonable light curve. So the regularization I'm adding is the smoothness regularization because we want the light curve to not change abruptly, like what I just said, with that singularity. So the smoothness regularization I'm using is the total variation penalty, which, if I rephrase it, is basically an L1 penalty on the derivative of the reconstructed light curve. One can obviously use other type of penalties on the gradient. For example, the L2 penalty. But I'm using L1 penalty because L1 encourages sparsity and allows large values at some points. For example, for this event file, we think that the light curve might have a very sudden change at this flare region. And L1 penalty actually can allow that, and it handles this better than L2 penalty.
Can I ask, so this total variation penalty that you have
Mhm.
would not deal with that scenario that you described for the left-hand panel, where it's zero between the units.
Yeah, exactly. So that is what I'm going to talk about
Okay,
also.
all right,
Yeah.
sorry.
I'm using two total variation penalties. One is because for total variation penalty you need a set of points, right? I'm using two set of points. One set of points is the arrival times, and another set of points is the uniform points outside of the arrivals. So I'm combining these two set of points and calculate total variation. That prevents those type of things from happening.
Excuse me, I'd like to ask why you need smoothness. You say you need to add smoothness. So what is the reason? You said earlier that this was an infinite resolution procedure, which is sort of contradictory. So is there something about what you're going to do with the result that it imposes you need smoothness?
So infinite resolution is like its nature. So basically you can do whatever dense set of points you have to calculate the total variation. It doesn't affect the resolution. So the reason this is needed is because, like the example I'm showing earlier, consider like a hypothesis light curve where it only has positive values at these arrival times and have zero elsewhere. This is very unlikely, but it actually has a very high likelihood. This penalty is basically prevent those fitting from happening.
So is it, sorry, maybe I'm gonna say this in completely incorrect terms for statisticians, but is this regularization a way to prevent the model to overfit the Poisson noise?
Yeah, exactly.
Okay.
So, sorry, I hate to push on this, but often at this point, people invoke smoothness, but then at the end, what they do with the result, if you look at it carefully, you could do the same analysis with the unsmooth data, with unbinned data. So I guess what I'm really asking is, in the end, do you really need smooth data, or could you do the analysis you're about to tell us about with unbinned data?
I probably need to do some clarification. I'm not doing anything to the data. This penalty is put on the light curve, which I haven't reconstructed yet.
Okay.
It's a loss function that I'm going to put on the light curve.
Okay, sorry. Go ahead.
Yeah. And like these binions, I'm just showing them for display reasons. They are actually just time values. I haven't do anything with the time values yet.
Now, one of the points I'm trying to get at is shown by the upper right plot here. It's typical of a bursting phenomenon in astronomy, like gamma ray bursts. the rise time is extremely sharp. And so if you smooth that out, you're destroying some astrophysically important information. So
Yeah, you'll see later that this type of very strong signals are not going to be smoothed out. Well, obviously, you need to tune the parameters. You need to tune like how large you want to put the weight on the penalty. But with some careful tuning, you'll see later that these type of variations on the left can be smoothed out. But this type of important variations is remain.
But Yanke, that was your point that using L1, right? L2 will be doing more damage.
Yeah, exactly.
The L1 would allow, smooth out the kind of low ones, but the high one would allow.
Yeah.
That's exactly what
That's my point.
Yeah.
Okay, if there's no more questions, so just as a recap, now I have this light curve R to be fitted. But suppose we have R, then we can compute a loss function that is a combination of negative log likelihood and this total variation penalty. So the next step is how do we actually fit a light curve given this loss function, right? Recall that the Gregory-Loretto algorithm consider all the stepwise light curve up to some, let's say 20 things. So it's definitely one way, which is we use some parameterized basis function. This basis can be the basis of all stepwise functions, or can use some fancy basis like Fourier basis or Wavelet basis. But it has some limitations. For example, if you use stepwise light curve, then its resolution is limited. If you use some other type of basis, you need domain knowledge. For example, if you fit it with a Fourier basis or something.
So this is the basis for R?
Yeah, basis for R, like how do you fit R? So what I'm going to propose instead is to fit R by a neural network. This is actually becoming really popular in machine learning literature. You might hear like neural representation somewhere, or like neural field somewhere, or like neural operator. Basically, they're kind of equivalent. They're all approximating a function, in this case, the light curve, with a neural network. So instead of outputting the basis, the weight for all those bases, it's outputting a single value. So you input the time t into the neural network, and the neural network is going to yield the value of R at this time point t. So here you can see why the resolution is infinite, because this t can be any value. It doesn't have to be on a grid point. It can be any value, and the neural network is going to output the light curve at that time point. So the neural network obviously has some weight phi, but we all know that although this weight phi is still finite dimensional, but the neural network is like usually very powerful in approximating any kind of function. So this is almost like infinite resolution. Now I'm representing this with a neural network. I can just do gradient descent with a loss function that I defined in the previous two slides to fit this neural network. Right. However, there's a slight modification here. So the neural network I'm using is very standard, a ResNet with ReLU activation. However, the ResNet with ReLU activation is pretty linear, because it's either linear weights or ReLU, which is a piecewise linear function. So it's usually pretty hard to fit high frequency signals like this flare. So a modification that I'm doing here is that it's what is called positional encoding. This is actually invented by transformers, but people later find out it's pretty useful also in neural representations. So basically what I do here is that instead of feeding the original t, that is just a time value, I'm encoding t with some sines and cosines of different frequencies of t. And feeding this encoded t, which is a higher dimensional thing, into the neural network. So basically, I'm preparing different frequencies of T before fitting into the neural network. Then the neural network is just going to need to fit all those frequencies and also the original T. And it's just going to have a much easier time.
Let me see if I understand this. The T here is just, T here is the entire, all the time you have, or the T is just one number?
T is one number.
So you take one number and make it a whole vectorized.
Exactly.
So in what sense I see sine cosine, though that's the frequency, but in what sense that you're capturing the sine cosine in terms of all the things together?
Yeah, but I mean, this is one T, right? But like, if you want to reconstruct a whole light curve, you would probably need to input many T's.
Right.
Then like this sinusoidal encoding is going to be different for different values of T. It's going to create different signals for the neural network to capture.
But this seems like distributing one T to a long vector. I think L here is what's the L? What is it?
L is like a parameter that you can choose. It's like the number of frequencies you want to put into the positional encoding.
This is very interesting. I'm trying to understand what's the intuition here.
Yeah, imagine if you want to fit this curve with a linear function, or like a piecewise linear function, you're going to have a hard time because you need like very fine grid of linear thing.
Sure.
That's like the intuition you can think of if you want to fit with a ReLU number.
Yeah.
You need a very large number. But if you do some Fourier basis of this before fitting, say for example, it's much easier to fit with a Fourier basis than a linear basis. Then the intuition is the same. If you do some Fourier transformation, I mean, obviously you also have a linear one, but you augment it with the Fourier transformation, then you will need a much smaller neural network to fit this.
Yeah. I mean, even if you are just fitting a linear regression, adding these things would give you a much more flexible model.
Yeah, exactly.
And identifiable as well.
Well, except David, it's a little bit hard to think about the linear, because you're essentially creating, technically speaking, all these terms are deterministic of each other, right? They're all functional of each other. So you're creating an enormous, I guess that's because when you have lots of T's, then there are essentially, I can see that, okay. So basically you're fitting a Fourier, you're doing a kind of discrete Fourier transform.
Yeah, you can think of it as that. But still, like all these features are fed into a neural network, so it can capture like some other type of phenomenon that this doesn't capture.
So in a transformer for text, the positional encoding helps the network understand the ordering of the tokens or whatever they're going to. In this case, in a sense, it doesn't need that information because you have the T itself, right? But you're just saying that just by adding this transformation, it would sort of help the neural network, knowing that ordering, in terms of the frequencies will help it learn much faster than if it didn't have. So your network, you could learn the same things you've learned even if you did not add the positional encoder. Is that correct?
That's a good point that I want to clarify. So in transformers, you can also only input the index, right? It also indicates the order without any positional encoding. Mm-hmm. But it just turns out that the transformers have a much harder time to learn. Why? Because first of all, it has different frequencies, and second of all, if you look at this, right, if you just input T is actually a value between 0 and big T. But the neural network is usually most efficient if all these inputs are like between 0 and 1, or like normalized. And all these sines and cosines are normalized. So it's basically a very, very useful trick for the neural network to have a better time fitting.
Do people try other bases? Then you don't have to do Fourier, right? Although that's pretty common with time.
Maybe some advanced research papers does this, but like it's pretty common for any neural representation papers to do this.
Okay. Thank you.
Basically, you have a T, you make it a sentence in terms of Fourier basis.
Yeah.
And then you improve
ResNet, which is what the models for sequence model?
No, not necessarily. You can think of it as an NLP. It's just a good NLP.
And
a good neural network. This is actually not I mean, it's a sequence, but it's fixed length. So you don't need any RN to do that.
I have a naive question. Is it the vector of all the times or just
it's
one?
A single time.
It's a single time?
Yeah.
Okay. So you encode the whole time vector with this. So it becomes an n-dimensional matrix?
Yeah, exactly. And this L, usually it doesn't need to be very large. I use 12. So this whole thing is 25 dimension.
Okay.
Yeah, just a short recap. What I'm doing here is that I'm already representing the true the light curve with a neural network, and I have defined a loss function. So now I can actually fit a neural network with the loss functions using gradient descent. So this half of the pipeline is complete, which gives me a very good light curve reconstruction result. You can see later how good it is. But remember our original motivation, right? We not only need to do the light curve reconstruction, but we also want to learn representations so that we can use those representations for learning tasks, right? And up to now, I only have reconstructed light curve. And obviously, I don't want to also take those light curves and feed into another RNN, which is kind of disjoint. So I want to learn them at the same time. Before I go into how I do this, let's take a step back and see how people in the machine learning literature usually do this. So probably the first representation learning method comes into your mind is autoencoders, right? Just a very quick recap on what autoencoder does. Let's say for images, you input an images into the autoencoder, which gives you a low initial latent, and then you input that latent into the decoder and tries to reconstruct the original image. So the whole thing is trained end-to-end with a reconstruction loss on the images. And then when this neural network is trained, the latents actually yield a good representation of all those images. Probably some semantic meanings like the different type of animals or different colors or something, an abstract, useful latent representation, which you can use for other tasks such as classification thing. So this is the typical autoencoder, but it actually doesn't directly work in our case. And why is that? Because our input and output are actually different things. Unlike images, you can just try to reconstruct the images from the output. Now we're trying to reconstruct the light curve. So our input is if this work, our input will be the event file, and our output will be the light curve, which is not exactly the same thing because the event file is very noisy, right? The light curve is supposedly the truth. There's two problems. First, the input, if it's an event file, has different length. So it's less steady or less stable. But people will say, well, I have RNNs for those, right? But usually RNN will success if the time series is it has pretty high signal to noise ratio, for example, text, or some time series. But notice that our event file is not exactly time series. It is a time series, but those values are arrival times, not intensities. So it's very noisy.
Yanke, would you mind stop sharing and sharing again? Some people have lost your.
Okay.
I've never lost your video, but I lose your audio from time to time. There's something strange today. I'm sure it's who knows what, but.
Okay.
Thank you.
Yeah.
That's good. Thanks.
Is it better now? Can people see it now?
Yes.
It sounds like, yeah.
I think if I click this
No,
button,
no,
someone
don't do
will
that. So, bring this thing on the right down a bit. So you see those bar and the,
Oh.
no, no, oops, no. Pull it, see those,
Oh, yeah.
yeah, that's
Okay. Yeah, where was I? Yeah, so basically I'm saying that the usual autoencoder doesn't quite work in our case. I've actually tried LSTM autoencoder and it doesn't fit at all. So what I'm going to propose instead is an autodecoder. For people that see it for the first time, it might take a while to understand. But basically what we do is that I'm just throwing the encoder part completely away. I'm just using the decoders. So in autoencoder, the latents are calculated through the encoder part. But in autodecoder, these latents are directly prepared. In the sense that, say I have n number of event files. I'm going to prepare n latents, which are initialized randomly, but I'm going to fit these latents through gradient descent. So,
sorry, you said you have the same number of latents as you have events?
Event files.
Oh, event files.
Yeah,
oh, okay.
same number of latents as event files.
Yeah, because the latent will be of a fixed length, right?
Yeah, it will be a fixed length. So for each event file, I'm grabbing the latents that corresponds to that event file, which is, say, this blue latent here. I'm passing that through autodecoder, which is a ResNet, and the output, I can compute the loss. The output is supposedly the lie curve. I can compute the loss between the lie curve and the event file through the Poisson likelihood and total variation, which I just defined earlier. I'm back propagating the gradient computed from that loss to both the neural network and the latents. So these latents are updated frequently through gradient descent. Maybe take a while to absorb this.
So in a way, take a classical analogy here. You are kind of fitting the missing data and the parameter together. It's like a gift sample scheme, right? You have the model, you can do the missing data, all the latent variable. Once you have the latent variable, you can fit the model, you can kind of iterate.
Yeah.
That's the idea.
Yeah, exactly. I'm fitting two things.
What are the parameters?
What are the parameters? I have two parameters here, right? One set of parameters is this neural network. But this neural network is shared. There's only one neural network. And the second set of parameters are these latents. So basically, this one single neural network captures the similar patterns of all those event paths, or maybe lie curves. And the individual latents indicates which type of lie curve it is.
Yeah, it's like a fitting the mixture model using this data augmentation idea. Thinking about the membership is the missing data. If you know which component, then it's fitting the regular likelihood. But then once you have the likelihood, the model, you try to estimate what's the membership, how you reassign it.
There's an infinite number of possibilities.
Yeah, but that's just like when you fit these, yes, the mixture model is like, it's a finite mixture, you can do that. But even if it's a continuous mixture, like a convolution, you can still do a sampling. Right? The sampling scheme still works. It's like, sample, you only sample one and you iterate the Monte Carlo simulation.
Yeah, exactly. Very good interpretation. So this.
So, sorry.
Oh, okay.
By the way, I'm working with Yanke, but I am also learning from his talk. So you're learning the weights of the ResNets, and then you're also learning a number of individual latent values for a batch of examples that you've passed during the training.
Yeah.
Okay. And typically, how many examples do you pass in the batch?
My batch size is 64. But I mean, these latents, I have one latent for every event file.
Right.
So if I have a million event files, I'll have a million latents.
So do you assume a typical distribution on the latents?
Yes, I'm going to talk about it soon, but it doesn't quite matter. It's like the prior, when you have enough data, the prior doesn't really matter. Yeah.
So you don't have a neural network get the latency
Yeah, exactly. I don't have an encoder to prepare the latent anymore. Because this autodecoder is kind of special, so it also has a special test time procedure. Remember in the auto.
Sorry, can I have one question? So how then would you do it for like a new data point?
Yeah, I'm just talking about it right now. So for a new data point, right? Remember for autoencoder, for a new data point, you just need to pass it through the encoder and get a new latent. But for the autodecoder, you don't have the encoder, right? So what you do is, this network is trained, so you freeze this network, and you initialize a new latent, and you only do gradient descent on this newly initialized latent on the new test point, new test data, and that's going to yield a new latent for your test data.
So you have to do gradient descent for the inference part as well.
Yeah,
for the prediction
exactly.
phase.
But now this is much faster because all your neural network is frozen, and your latent is only, say, I'm using 8-dimensional, so it's fitting much faster. Although it's still slower than encoder.
So can the way I'm thinking about trying to think of statistically what you're doing, right? Is that just now you treat the latent themselves? Now you have you have the model itself, all the parameters, what you want to do. You have the latents, but because you have multiple latents, you can also do one at a time, doing one condition on everything else. Is that what you're doing? Because when you do you can do all the latent together, or you can have one latent given others, given other models. It's like a higher give sample type of thing.
No, I'm not conditioning on other latents. I'm conditioning on this neural network.
Oh, so then you're doing the marginal in a way. Just integrate the other latent. Why not condition other latent? Would that be better or that's worse?
Probably not, because different event files are supposedly independent.
Oh, so you don't have to. Okay.
Yeah.
You're saying condition on the models, the latents are independent of each other.
Yeah.
Therefore, you look their condition and condition will be the same.
I'm not claiming it's the same, but I'm just not using it.
Okay.
Yeah. Another way to think of the test time optimization in terms of Gaussian mixtures for statistician is now you fit the Gaussian mixtures and you assume the means and covariance are fixed, are trained right now. Given a new data point, you decide what's the cluster it should belong to.
Yeah.
Those are the latents that I'm trying to optimize for.
Sorry.
Oh, yeah. Yeah, let me know if there are further questions, but before that, this is the complete pipeline that I introduced. So this is actually an illustration of the full pipeline. I'm going to reiterate. So you first, given any single time t, you do a sinusoidal embedding of different sines and cosines to produce a fixed length vector gamma. Now you prepare a latent randomly, and you concatenate this t, gamma t, and this latent. You feed them into the ResNet. It's going to output a single value, which is the lie curve value at this time t. That's for single t. Now you can sample many t, which gives you a lie curve. And now you compute this lie curve, the loss function of this lie curve, and the event files. And this is your data. I'm not doing anything for your data, just compute the loss. The loss is going to be shown in the next slide. But you can backpropagate this loss, backpropagate the gradients through both the ResNet and the latent.
So for statisticians or others who want to do statistics, I think this is what I would call it's like the complete data fitting model. You pretend you know the latent.
Yeah.
And then you just whatever ResNet doing is just the optimization model procedure. So now you get the parameter you want, or in this case line curve.
Yeah.
But then you have a next step is going to get the latent itself.
They're done at the same time.
Right, no, but it's this, but your output itself, there's no latent in it, right?
Yeah, exactly.
So the next run, when you're going back to do the back propagation, you're going to get the latent.
Yeah, because you need to train the neural network through back propagation. But these latents are stored, right? So when this whole training is completed, all these latents are
still there. You just don't represent them, but it's actually there.
Yeah, exactly.
And just so I understand that the T and the gamma T over there is actually Ti. I mean, it's for all T.
For all T, not Ti. So these Ti are arrival times,
Right.
and this T can be any. It can be one of those arrivals, and it can be other things.
But that's the input, right?
That's the input.
So it
yeah.
has to be for actual arrival.
No, not necessarily, because you will need some other outside points to calculate, for example, the total variation and that integral, if you remember from the loss function. Yeah. Speaking of loss functions, now this is the full formula for loss functions. Remember, right now I've ignored the energy bins, but it's like pretty easy to add back those because in astronomy, people usually just bin the energies into three: soft, medium, and hard. So now instead of one value, I can just output three values for each energy bin. So the loss has three parts: negative likelihood, which I've introduced earlier. We have two terms, this term and this term for the integral. We have the total variation, which has two parts because I'm using two grid points. And finally, I have a kind of a L2 normalization on the latents. This is from Sheldon's question. It's basically equivalent to Gaussian prior on the latents. But what kind of prior doesn't really matter because once these are strong enough in the latent, the prior doesn't really matter. But this just prevents the latent from going crazy to infinite or something.
So, this again is statistical interpretation of the L1 here. Think about difference between L1 and L2. Think about the pi. L2 is a normal pi. The tail is a light, the three standard deviation, you can't go out that much. The L1 pi is a Laplace pi, which is exponential, which is a much longer tail. That's why it allows, once in a while, something go crazy, and the other one is much more regulated. So if you think about it from the basic perspective, it's very clear why L1 does a better job. Now, from there, you say, well, if I want something even crazier, well, you can do whatever the pi you want to have even longer tail. You can do a Pareto tail. Probably it's too crazy, right? It's, polynomial decay, so you can do all sorts of things. But I guess that if we really wanted the training, I think this is already good enough, but it doesn't hurt if you want to slash in some other parameters on the LP and tuning that as well, or the latent product have an LP norm. And tuning that as well, exactly. Which is it's only two more, who cares, right? Then we can tune many things. It might be there's some tiny gain, but probably not much.
You can even fit the position of the sinusoidal encoding. You can even let that to be a variable.
Yeah, it's true. You can
there's many things you can fit. That's the complete pipeline. And just to reiterate, at training, I'm fitting both the neural network weights phi and the training latents. And at test time, I'm fixing these neural network weights. I'm only fitting a new latent for the new event file that I'm interested in.
So, Yanke, there is one interesting point here I want to raise. And in the general classical statistics, like we do not try to optimize over latent variables. Because if you optimize latent variables, like maximize them, it's essentially like minimizing them, right? But that you will be overfitting. So for latent variables, you do integration, right? It's a marginalization because latent variable you marginalize. Now, because you're doing L2, in L2, I think that the marginalized over, because the L2 is everything the mean, right? So I think it's fine. It's maximizing. It's getting the mode is the same as getting the mean for the normal thing. So it kind of works. You can do this, but more broadly, if you do something else for the latent variable, then it doesn't fit this framework. But now you have to integrate them out, which is much harder, I guess.
Yeah, exactly. That's the difference between variational encoder and autoencoder.
Right.
You can probably also do a variational autodecoder. But it's just a different thing. So that one you have a distribution over the line curves. Like here I'm just using the MAP, the line curve.
I do have to leave now, sorry. Thank you
Thank
so
you.
much. And I hope you get to the part where you show how these representations are used for the downstream tasks.
Yeah. I'm gonna show pretty soon.
Sorry.
No problem.
Yeah, thank you
Thanks
so
for
much.
coming.
Yeah, no, my pleasure. Thank you, Yanke, for nice work. See you later.
So
Yeah.
now comes the probably more interesting part, which is the experiment results. I'm taking my pipeline and I'm fitting about 100,000 event files from the Chandra Source Catalog. I'm doing some minimal pre-processing. For example, I'm truncating all event files into 8 hours because otherwise it's not an apple-to-apple comparison. I'm getting into 3 energy bins as basically all people do in astronomy. So here are the light curve reconstruction results for the 4 event files that I showed earlier. So we can see that for those very, very large features like this flare, this dip, and these periodic sources, it almost fits them like pretty well. And for those noises, for example, these variations, and especially this seemingly homogeneous Poisson process, it's doing a good job by like, I think probably the total variation is doing a good job by not overfitting to the noise. But still, like there's some not imperfect results. For example, this high energy band of this dip. I would imagine a better fit would be like a more flat, but there's
So two things, the fact that these are being considered soft, medium, and hard, they're just 3 different, completely independent data sets. Right? There's nothing, you're not combining information across the data sets.
Yeah, no, but like I'm kind of combining them because the neural networks share.
Sure, but as far as the neural network knows, there is,
soft
does not mean anything.
Yeah.
Hard does not mean anything. It's just,
it's
just another data set.
Kind of. I'm splitting one event file into 3, soft, medium, high. And total, I'm just adding them up.
So I want to see that the results you're showing, is that average over many runs or just from one run? Like,
From one run, because one run takes like 2 weeks.
Oh,
I see.
I mean, the whole thing needs to be fitted through gradient descent, right?
But well, I know, but that's a harder question. But usually those things, if you run again, you may get a very different answer, right? But there could be lots of local modes, or you don't experience that.
No, I mean they could be slightly different, but it's impossible that another round just miss this curve. Like
No, these are good ones, but I mean for these bad ones.
Oh, you mean this one?
Yeah. Is that if you run again, would that be? Because usually people run to 20 average or something.
Yeah, it's possible. I would say, yeah. But like this happens for all machine learning models.
Why does it take so long to run?
Oh, well, because we're fitting a neural network.
Neural networks don't usually take weeks.
These are Harvard neural network. Harvard's on a very slow scale.
I don't have the best GPUs to do, but like
you need to buy him some NVIDIA GPUs, Charlie.
Are you using you're not running on your own machine, right?
No, I'm using some cluster, but it's V100. It's not like A100 or like H100.
So those potentially can be improved.
Yeah, definitely.
Okay.
Also, I mean, you could cut down the number of data sets that you're using. You don't have to use 8 others, you could use just 1.
Yeah, actually, one of my earlier experiments just used 10,000 of like potentially good event files, and those are much better. Yeah.
Sorry, I missed the part where the training time. I looked that it was 8 hours.
No, that was like I truncated the event files into 8 hours.
Oh, I didn't, and it took weeks to train?
I can probably optimize, but like I just don't have.
I mean, yeah.
I hope people can optimize that later.
Yeah.
I have a question about your training data. So you said you have 10 to the 5 event files.
Right.
Do you remember by how many orders of magnitude the total count rate in those event files varied within the 8 hours that you picked Some
a
very
lot,
few counts.
like as few as less than 10, as much as 10,000.
Okay.
Yeah.
Thanks.
But yeah, because of this AutoDecoder thing, we don't have to worry about different number of counts anymore.
Yanke, I have a naive question again, but just to like seeing if I understood correctly. So what the neural net is doing is trying to reproduce what a Gregory Loredo feed does to a light curve in X-rays, but faster.
Not necessarily fast, maybe. Yeah.
Maybe faster.
Because now I'm fitting all these together, it takes 2 weeks. If it only fits one, probably faster.
But yeah, training, but inferring, is it faster?
I need to time it. Yeah, probably faster than very Loredo, because now
it's
just
also quite a bit more general, right? You're not they're fitting a what do you call it, a histogram.
Yeah, they're fitting stepwise. Now
Stepwise constant, yeah.
Yeah, this is, yeah, you can see it's pretty smooth.
Right, so if you wanted to compare it more directly with that algorithm, you wouldn't need the classifier, right? It would be just the first part of your algorithm where you're fitting the light curve.
Yeah, I don't need latents anymore. If it's just one event file, I can just fit the neural network.
So that would be, I expect, would be quite quick.
Yeah.
How large is the neural network?
A couple million parameters. It's this 100,000 event files that takes long because I need to prepare one latent for every of that. I mean, training time, but at test time it should be quicker.
Also, it is data processing that takes a lot of time.
Well, no, it doesn't take any time.
Oh, I mean preparing the embeddings, the encodings. Is that what takes time? Or
it doesn't, well, because I need to backpropagate the gradient into every latent, and I have a million of them. Like 100,000 of them.
Yeah, okay, so the training is...
Yeah.
Okay.
That's actually...
Jeff Scargill's left now, but he unsurprisingly was comparing what you're doing to Bayesian blocks, which is his favorite algorithm.
Oh, is that in the chat?
It's in the chat.
I'm not exactly sure what Bayesian block is. Yeah, but I think Bayesian block is basically Gregory Loredo, right?
No, Bayesian blocks is a change point algorithm.
Oh, okay.
So
but I mean, it's also a stepwise constant fit. It's just it has a Bayes factor in there to decide how many steps to put in it.
Okay. Those are, like, I would say, theoretically more robust algorithms than this, but the advantage of this is it also creates a representation, which I'm going to show pretty soon.
So,
right, and also you have, I mean, don't sell yourself short. That this highly non-parametric light curve, even without all the classification, right? That's kind of cool.
Yeah.
So the second from the top in the periodic and the first to the top in non-varying, they look very similar. And the second half of the periodic looks very similar to the non-varying. Why is it that the periodic did pick up the fluctuations, but the one in the non-varying did not?
Because here's the thing. They have the same latent, right? So this is one event file. Although I split it into 3, it's basically one event file.
So they are being considered as one set.
Yeah, they're being considered as one set.
It knows that
it's hierarchical in that regard.
Okay.
Yeah, exactly. So it knows from the latent is kind of periodic.
So it's borrowing information from the set, from the high.
Yeah, no, this is really nice. Because I mean, you're using these neural networks for these highly non-parametric things, but the model itself is quite statistical.
Yeah, thanks for that. Yeah, it has some statistics.
I think that's what the initial idea was, like to see if a neural net could actually learn the Poisson process that is in this kind of counts. So I think it's great as well.
Yeah. Okay. Here's a still equally interesting part. So remember, that was just like a reconstruction. But now I have those learned latents that I can do interesting things with. So here is like a visualization of, on the top is PCA, on the bottom is t-SNE of those latents. So the latent has dimension 8. I'm just projecting into dimension 2. So on the top is PCA versus hardness ratios. Where hardness ratios, some meaningful physical quantity. So we can see that there's a very non-trivial trends of hardness ratios in the PCA space. And on the bottom is variability index, variability probabilities computed from Gregory-Loreto, plotted against t-SNE. So we can see that there is some obvious clustering of the more variable sources, which are the brighter ones. They're all like clustered, relatively clustered together. So this is basically showing that the learned latents contain some interesting and useful abstract information that has some correlation with the variables that we're more familiar with. Now I'm going to do some more quantitative tasks, which, sorry, this is stuck. Yeah, I'm trying to use the learned latents to do some regression and classification predictions. I'm trying to, in order to show that these latents are very powerful, I'm just using a random forest with 100 trees without tuning any other parameters. So I'm basically take a vanilla model and fitting these on these tasks. So these tasks I'm doing is like I'm predicting the hardness ratio. I'm predicting whether the source is variable. By definition, I'm saying the source is variable if its variability index is greater than 5. I'm trying to predict the source type, 1 out of 7, which is a relatively harder task. I'm also doing the easier task where I'm just trying to predict YSO versus AGN, which is a binary classification. I'm doing a 80%, 20% train test split. I'm not doing any cross-validation, just like single run. And these results are the test results. So it's actually quite good. If you compare these classification accuracy with those earlier papers where they use hand design features and they tune their classifiers like a lot. I'm not tuning anything. These are actually comparable results. So I imagine with more tuning on both the PPAD pipeline, that is my pipeline, or if you tune more on the small classifiers you use, you can probably get higher results.
So just to understand, so for example, for the YSO versus AGM role, what that means is that you're taking the subset which have been classified as YSO or AGM, and then looking at the accuracy just for that sample.
Yeah, and for that sample, I'm splitting with train and test. I'm training a random forest classifier, test on the other part.
Okay.
Yeah.
Where do you get the classification from?
I get the labels from one of the previous paper, like Yang et al. Paper, where they have some label, where these labels are created by
the training set?
Yeah.
Yeah.
Not the trainings. The training set only has like 20,000.
2,000.
2,000.
Yeah, it's down 2,000 label.
So we just with 2,000, you are able to get an accuracy of 75%. Is that?
Yeah, within those 2,000 labeled sources. Yeah. But I mean, there's many other sources without labels, which I cannot verify accuracy.
Pretty good.
This is really promising. Yeah.
I know.
Yeah. Well, second to last slide. This is anomaly detection. What I do is I have this target source. These are the reconstructed lacquer for 3 energy bands. So I have this source as a target in mind. In the latent space, I'm finding those nearest neighbors in terms of latents, and I'm plotting the reconstructed lacquer for these 7 nearest neighbors. And we can see that a lot of them actually also have fair-like behavior, such as this one.
Nearest neighbor in which space?
In latent space.
What latent space? How do you find nearest?
Just L2 distance nearest neighbor. latent space. Yeah, I would say most of them, like this one, this one, this one, this one, they all have some flare-like behavior. So we could potentially also find, say, if we want to find flares, we can do like a target latent and just see its nearest neighbors and potentially find some other flares in this way. So yeah, that's pretty much all my talk today, and like some future directions. First of all, like I said, this is not optimally tuned. So I hope like if someone has more resources, you can like scale things up in terms of both the network size and the number of data you can fit and tune better. Second one is like we can actually do some meaningful downstream tasks. Is the results I showed, they're trained using the known labels from humans. But for those unlabeled things, we can probably, if we trust this pipeline, we can predict the labels for those. And finally, this is probably a more research interest, is like actually consider autoencoders. So like one of the probably most important drawback for autodecoders is that at test time, you still need to optimize the latent, which is slower than autoencoders. But as I said, the event files are like different in counts, and they are very noisy. So I'm not sure how to bring back autoencoders yet at this moment, but it's definitely an interesting future direction. Yeah, that wraps up my talk today.
Excellent. We made a lot of progress. It's
Yes.
very nice. Yes, this is a good education for all of us. So, questions? More questions? Yes.
No, I was just waving at the camera.
David has.
I can go after.
No, you can.
Oh, okay. So in the numbers that you quote for accuracy F1, how balanced is the data set?
It's some of them is more balanced, some of them not. So for YSO versus AGN, it's pretty balanced. And for 7 class, it's pretty unbalanced. For some of the classes, it only has less than 10 labels. But I skipped that, but I did SMOLT, which is a rebalanced thing for training. Yeah. But people can probably do better things because I didn't tune the classifier at all.
I think this is great. Congrats. And I'm wondering that just as a final product, it would be amazing. Like I think you've shown that the representations are meaningful already in some way. Like you can do classification and you can do, for example, anomaly detection. So for for production use for the X-ray astronomers, it would be great if, for example, an astronomer interested in a particular Chandra source. Maybe they don't want to go to the event file, but they have the source ID. You can, in some way, like attach a source ID to each of your event files, so you have a representation, and you can already like put in a web page, and astronomers can just easily download the representation. So, right? Or fetch it through Python or something. You know?
It's already there. So
it's already there.
The observation ID is already stored in.
Oh, great! You are steps ahead. Yeah. Amazing. That's one use. Another, well, is use inputting also the event file if someone is interested in getting the representation, because that will be really useful for example, for other tasks that we can't even imagine now. For example, but those are usually classification, anomaly detection. But let's say that there are other tasks and where your representations could be useful. So, yeah, okay. I just wanted to say that, propose that.
One thing on addition I have. So you get these light curve representations. What about uncertainty bands? Is that an easy way to get that?
Not very easy at this point. Unless you want to fit the neural network 20 times. But like you can potentially do variational autodecoder. I'm not sure if it exists right now.
No, I mean, so let's say you train the network already. Right?
Yeah.
So, using that, is there some other bootstrap or something?
No, not a straightforward way. But like theoretically, if you change this to a variation of a decoder, then it's basically like a Bayesian posterior. Right now it's just the maximum posterior, but you can also do like the full posterior likelihood.
Other questions?
Well, we have reached 1:30, it's the time to sign off, so.
Yeah, well, perfect. I want to thank Yanke for great work. You started this about a year ago, is it?
Yeah.
About a year ago, yeah. And I think this also should encourage other students to work on these kind of problems, because this group is trying to get into machine learning. And I think of what makes the success for you, I think, is the combination of the machine learning and your statistical, modeling thinking, all this together, right? And there's a lot of these choices, L1, L2. Those you can do by try and error, or you can do it because you understand the principle, right? The long tail was short tail, so we can do those things. So I think I would definitely encourage more students to take on a project like this. You learn something incredibly important and it's useful, because astronomers like you guys will take over to actually use them, right? Yeah. So well, congratulations. Now you haven't written this thing as a paper yet?
It's ongoing.
Okay, yeah, get this thing done, because that's important.
Yeah.
The other thing working in this area, you have to do fast. Everybody else is working. If you don't push it, other people can push it. So I would say get the first paper done. You already have plenty. Then work on the second one, whatever further, develop the methodologies if you want to, right? All the coding part.
I guess I have to leave it to other guys because I'm graduating soon.
Well, we can hold your degree if you want to. That's a
you
we have,
I don't think you want that.
Yeah, but thank you. Yeah, but
Thank you.
it's good that we will need to save your everything, your code, and everything, so the next person can take out. But,
Yeah.
great.
All right.
Right.
Okay.
Let's thank Yanke again.
Thank you.
Yeah. Wonderful. Great.